Hello, everyone. We're going to go ahead and go over section 9.2, which is on triangles. So as an overview, what are some of the most iconic triangular shapes in the real world? Triangles have more applications in real world problems than you'd really think. So some very famous triangles and big things, like the Louvre in Paris. I don't know if I said that right. Then we also have like the pyramids. These are triangular shapes. They are pyramid shapes, so they do have a square bottom, but they are triangular on all sides. Another famous triangle is the Twilight Love Triangle. Sorry. Intro to triangles. So a triangle is a closed geometric figure that has three sides and three angles. Closed just means that you can trace the entire shape without raising your pen or pencil off the paper, so like a continuous image. So it has three sides and three angles. So we see each one of these sides are the length sides there, and each inner corner here is called an angle. The three sides of the triangle are the line segments. So the line segment version of the triangle. So that's how you draw the triangle. You draw the line segments, connect them. The points where the sides intersect are called the vertices, or the plural is the vertex. So the vertices, or the singular is vertex. So vertices are each one of these points here at the edges, but those inner corners are called the angles. So the inner corners there are angles. And angle measurements are measured in degree, so like a degree of opening. So just how much it's, kind of far away from the previous line or the line next to it. That's an intro to triangles. There are three types of triangles, and this is categorized by sides. So when we have types of triangles, we'll categorize them by sides and by their angles. And so since they're two different categories, they can be two of each. So it can be, categorized by the sides, and by the angles. So it can kind of be two things, but if it's the sides that we're talking about, we're not talking about the same ones. But all right, so starting off, we have the isosceles triangle. So an isosceles triangle has at least two sides of the same length. So something like this, where each one of these sides are a bit longer than maybe the base. Then we have an equilateral triangle. It would be that all three sides are the exact same length. So it is equal in equilateral triangle. Then we have a scalene triangle. It has three different lengths. So every length of the sides of the triangle are all different. So those are the three types of triangles based on their sides. Hopefully this should be a little bit of a review. But if not, there we go. That's what they are. Isosceles triangles are two sides of the same length. Equilateral is each side has the same length. And scalene is that none of the sides have the same length. All right. So we have this example. All of my sides are equal. What am I? This would be an equilateral triangle. Equilateral triangle, because all the sides are equal. Then we have all of our sides are different. What are we? So there's two of them now. All their sides are different. Well, they're scalene triangles. So having each side be different lengths. Scalene. Two of my sides are equal. What am I? Very happy triangle here. This is an isosceles triangle. So isosceles triangles kind of tend to have a very tall or a very short kind of look to them, since two of their sides will match. All right, so those are the different categories of types of triangles based on their sides. So now we have types of triangles based on their angles. So we say an acute triangle is, or an acute triangle has three acute angles. Acute means less than 90 degrees. So each angle is less than that 90 degree. Remember, 90 degrees, that right angle, the one that is exactly like perpendicular, it makes that little box. So an acute triangle would be less than that angle, so smaller than those angles. So this would be considered an acute triangle here. Then we have right triangles. So a right triangle has one right angle, which is exactly 90 degrees. They'll be indicated with the little box most often to indicate that that is exactly 90 degrees. The other two angle measurements can be whatever they, whatever they are. But the one in the middle is exactly 90 degrees there, the little box, the right triangle. Then we have an obtuse triangle. So an obtuse triangle has one obtuse angle, means greater than 90 degrees and less than 180 degrees. Triangles are only made of 180 degrees, so it can't be more than 180 degrees. It would no longer be a triangle. So greater than 90, greater than that right angle, but not 180 degrees. So this is an obtuse angle, one obtuse angle. This would be that obtuse angle here because it is opening up wider than 90 degrees. So as long as there's one obtuse angle, it is an obtuse triangle. An acute triangle has to be that all three angles are less than 90, and a right triangle means that one angle is a right angle, 90 degrees. So those are the different types of triangles based on angles. And like we said before, we can categorize types of triangles by their sides and their angles. This is what we're about to see. So these are scalene triangles. We've already established that from before, but because all their side lengths are different, they're scalene, but what are they also based on their angles? We can see in here, these angles, these are more than 90 degrees, and there only needs to be one to make them obtuse triangles. So these are scalene triangles and also obtuse triangles. So you can categorize triangles by kind of each category, sides, and angles. So this, I'm an equilateral triangle because all my sides are the same. We already established that. But what am I based on my angles? So if we look in here, we said that right triangles would be indicated with a box. So in this case, we don't see any of those. They all look fairly small, smaller than 90, which would make this an acute triangle. So this is an equilateral triangle, which is also an acute triangle. Then my head represents what type of triangle. So we have Phineas from Phineas and Ferb here. He's got a very angular head. And there's no box in here, but that is very clearly perpendicular, making his head a right triangle. So we see that like one going exactly up, exactly horizontally, and then the hypotenuse that kind of cuts across. This is a right triangle here. This inner angle here would be 90 degrees. So, all right, those are the different types of triangles. Now we go into triangle facts. So the sum of angle measurements in a triangle, we say in any triangle, the measures of the three angles will add up to 180 degrees. We said that triangles are 180 degrees in total, so they can't be any larger than 180 degrees. And so their angle measurements will all add to 180. Then we have the Pythagorean theorem. So the Pythagorean theorem states that the sum of the squares of the lengths of the two legs in a right triangle always equals the square of the length of the hypotenuse. So looking at our picture here, the hypotenuse is the diagonal portion. The legs are the two like vertical and horizontal sides. It doesn't really matter which one you label as A or B. Just remember the legs are the vertical and horizontal sides. So we're saying that the square of them, the sum of the squares, so raising them each to the exponent of 2, adding them together, would equal the length of the hypotenuse squared as well. So if we use A and B to represent the lengths of the legs and C to represent the length of the hypotenuse, we get this figure and this equation. A squared plus B squared equals C squared. So if you want to find the hypotenuse, you can plug your values in and solve for C. It is squared, which means you need to take a square root to find C. We say in addition, if the sides of any triangle satisfies this equation as well, it is also a right triangle. So if any sides would satisfy this, whether or not you were told it was a right triangle, if it satisfies, it inherently becomes a right triangle then as well. So, all right. Let's go ahead and find the next example. We're going to find the measure of the angle C in the following triangle. We have our triangle here. We have A, B, and C. These inner corners here, these angles for A and B are both 40 degrees. We want to figure out what the angle is of C. So there's no box, there's no clear indication of any box in here, so this is not a right triangle. But we do know that the sum of the angle measurements will equal 180 degrees. So we say if A, B, and C are all the angle measurements of the given triangle, A plus B plus C should equal 180 degrees. We know that A and B are both 40 degrees. So inputting those values into our equation there for A plus B plus C equals 180, we get 40 degrees plus 40 degrees plus C equals 180. We want to solve for C. Simplifying that, we get 80 degrees plus C is equal to 180 degrees. To solve for C, we subtract 80 degrees from both sides. To get the C would be 100 degrees. So this value right here would be 100 degrees. 100 degrees is greater than 90 degrees, which automatically makes this triangle an obtuse triangle. And an isosceles as well. All right, so that wraps up that example. Let's do another one together. So we want to, in this case, we want to build the frame for the roof of a shed. The carpenter must cut a 2x4 to fit on the diagonal. If the length of the horizontal beam is 12 feet and the height is 3, we want to find the length of the diagonal beam. So we're buying a 2x4 to fit in the diagonal, but we need to actually know how long that diagonal is going to be. We're told that horizontal beam that goes all the way across is 12 feet. The height is 3. So we can go ahead and find the hypotenuse beam, essentially. So let's go ahead and do this together. All right. For our example here, we are told that we're building this frame for the roof of a shed. It's very beneficial to try to draw a picture to get a better idea of what's going on. All right, there's an image. So here's our image of our shed. It's gonna look something like this. We know that the part that we're focusing on here is the roof portion. So we're focused on this chunk right in here. So we're gonna go ahead, kind of isolate that portion. We've got our roof. Probably looks something along this line here. And then we're given some information. We're told that the horizontal beam that goes across is 12 feet. Then we're told that there is a vertical beam that goes right through the center as well. So there's a beam here. And this beam is 3 feet. And we want to know what's this length of the diagonal beam there. Don't know. Question mark feet. Don't really know. If we want to find how long this diagonal beam should be, we see that our image here, our roof, kind of looks like two triangles put together. And even though the picture isn't wonderful here, this horizontal and vertical beam create a 90-degree angle. So this is a right triangle. And since it is a right triangle, technically two right triangles here, since it is technically two right triangles, we just need to find the length of that one diagonal beam, so we don't necessarily need to worry about a second triangle, but we do need to know the base of this triangle. The base of both triangles, in addition, is 12 feet. we say that this vertical beam is cutting it right in half, which would make this length here be 6 feet. So for our given triangle, our blue triangle in here, we've got 3 feet, what we're trying to find, and 6 feet. So these are the units that we'll use when trying to find that last length of our right triangle. Now remember, we want to remember our right triangle uses Pythagorean theorem. A squared plus B squared equals C squared. So we can label our lengths here. We can say this is A, B, and C. So we know what some of these lengths are. We know that A is 3, B is 6, and C we don't know. So we're trying to solve for C. So we can plug all of these into our formula. We get 3 squared plus 6 squared is equal to C squared. We're trying to solve for C, so let's simplify a little. 3 squared is 9. 6 squared is 36 is equal to C squared. Adding 9 to 36, we get C squared is 45. We're trying to find this value in feet. We need to find C and not C squared. So we can go ahead and take the square root of both sides. In this case, we have that C would be equal to the square root of 45. That doesn't really give us a whole lot of information. Remember, we want this in feet. So if we're measuring this, we kind of want this in maybe some whole numbers, decimals preferably. So we can go ahead in our calculator and type out the square root of 45. Let's go ahead and round to 1 decimal place. And this should give us 6.7 feet. So we want to find the length of that diagonal beam. That diagonal beam should be 6.7 feet. So if they're cutting a 2x4, it's not going to fit. So they'll need a much longer piece of wood there. You'll need it to be at least 6.7 feet. So really kind of like at least 7 probably to kind of trim it down, maybe 8. But there we go. So the length of the diagonal beam, 6.7 feet. So, all right, let's wrap up that example. So we're going back over to our lecture. Now, one additional way that we can solve things about triangle is using this method called similar triangles. So when you have 2 triangles that are pretty much the exact same shape, but different sizes, we call those similar triangles. When the 2 triangles are similar, their angles actually have the same measurements because the angle measurements do not depend on the lengths of the sides. We see that even if one is much smaller than another, their angle measurements end up being the same because they're the same shape. The angle measurements really only depend on kind of how far away those 2 lines are from each other. And if they're just scaled up, the angle stays the same. So this means that if corresponding angles have equal measures, that also means that the triangles have to be similar. So if it kind of works in other directions, so you can say that, if these triangles had equal measures, then they would also be similar triangles. So we can use these things to make certain problems, like how we'll see on our next example, but also to relate different sized triangles and kind of find out information that we need based on information from a bigger or maybe smaller similar triangle. So in this case, we're saying that the measure of A should be equal to the measure of A apostrophe. So between the two triangles here should be the same. The measure of B should be the same as B apostrophe, and the measure of C should be the same as C apostrophe. So all of these angles like will match each other. This also tells us that the side length ratios are also equal. So the length of side A to B is the length of side A apostrophe to B apostrophe, that these should be equal ratios. Same thing with length B to C should have an equal ratio to B apostrophe to C apostrophe. And that lastly, length from A to C, this length here should be the same ratio as the length from A apostrophe to C apostrophe. Now, all of these have the same ratios, meaning that they have the same angle measurements. So when we have similar triangles, we get to compare angle measurements and side lengths. So that's always a really helpful type of thing to know. So we can use similar triangles to kind of help us solve problems. Like our example. We say if a tree casts a shadow that's 12 feet long, and at the same time, a person who is 5 feet 10 inches tall casts a shadow of 5 feet. What's the height of the tree? So we have a tree casting a shadow and a person casting a shadow. So we're trying to find the height of that tree that is originally casting that shadow. We know how tall that person is, 5 feet 10 inches. So finding the height of that tree will then help us as well. So, all right, let's go ahead and do this example all together. So for this question here, we have two distinct triangles being made. This will really help us to draw a picture to really envision what's happening and maybe help us along the way to identify that this will be similar triangles. So let's go ahead and draw some pictures to represent this situation. So we've drawn some pictures here. We have our person who's casting a shadow, and then we have our tree that's also casting a shadow. So we have some information, so let's go ahead and fill in that information. We have that our person is 5 feet 10 inches and the shadow is 5 feet. So we can say that this length here is our shadow, and that's 5 feet. Then we know our person is 5 feet 10 inches tall. So 5 feet 10 inches. So we know that's how tall they are. We don't really know this value of the hypotenuse. We don't know what that would be. We don't really know what it would be in the context of the tree either. So let's just kind of ignore it for now and see if we can still figure out our problem without it. So moving on to the tree, we're told that the shadow of the tree is 12 feet long. So we're treating this length here as 12 feet long. So this is 12 feet. And what we don't know is the height of the tree. We don't know what this is. So height, we don't know. And this is what we're trying to find. And if we notice here in both of our scenarios, and this is how your scenarios are drawn, in both scenarios, they're creating right angle triangles here. They have the little boxes. These are both creating right angle triangles. So they're both creating right angle triangles. We are going to use the process of similar triangles to try to find the height of this tree. We are essentially banking on the fact that since they created that right angle triangle, we are going to just assume that these triangles have been scaled up and scaled down. So we're going to use similar triangles to help us find that last value there. So in this case, there's not a whole lot of like checking to see if I can do it. It's more of I'm going to use this to find that last value that I don't know of. And that is because they both have at least one of the same angles. They're very similar shapes. So we can kind of assume these are probably similar triangles. So, all right. So we have our person and we have our tree. We're trying to find the height of the tree. So remember what we said about having the lengths, the ratios of the lengths will be the same. So let's, for example, say that the shadow of our person is little a and the height of our person is little b. Then the shadow of our tree is capital A and the height, which we don't know, is going to be capital B. So in total here, we have that the height for the length of our shadow, we can pick whichever one here. Let's do that A over B. So we say that the length of person's shadow can be divided by the height. Spell that right. Yep. Height of person. That ratio should equal the same ratio for the tree. So the length of tree shadow should be the same ratio for the height of the tree. So these ratios should be the same. So we're going to set up this ratio here. And since we're making these kind of computations, we want to realize that the height of our person is given in feet and inches. We want this all to be in feet. So we need to convert 5 feet, 10 inches into all feet. In this case, we're just going to use a calculator. We're going to divide out 10 divided by 12 so we can get a ratio of that, the foot. Because we're in 10 inches, there's 12 inches in a foot. So 10 inches divided by 12 inches, add that onto the 5 feet. The length of or the height of our person here in all feet should be about 5 point, we're going to give it 3 decimal places because we're using this value in our calculations. We're not just going to kind of toss it off to the side or just finish up with it. So we're going to give it a couple more decimal places than we normally would, since we're using it to calculate things. So we're going to say it's about 5.833 feet. So we're going to go ahead and we're going to set up our ratios. So we're told that A, the shadow is 5. This is all in feet, so we don't necessarily need to write feet. And then we have that divided by the height of the person, which is 5.833. And we're setting this equal to the length of the tree shadow, which is 12, divided by the height of the tree, which we don't know yet. We're going to leave that as H. For our answer, we're going to leave that as H. So we can go ahead, and what we can do at this point, now that we have this equality set up, we want to know what H is. We can go ahead and we can cross multiply. So we can cross multiply, and we're going to go ahead and multiply those values out. So this will leave us with a 5 times H is equal to 12 times 5.833. If you multiply 12 by 5.833, you should get a value that is just exceedingly close to the number 70. We're going to round that to 70. So we're going to say, 12 times 5.833, incredibly close to 70. We're going to call it 70. So 5, H in this case is equal to 70. We want to solve for H. Go ahead, divide by 5 on both sides to get H. is equal to 14 feet. So we get h is equal to 14 feet. So the height of our tree would be 14 feet tall. So we want to know the height. 14 feet. That would be the height of our tree. So I was using similar triangles, so establishing that both of our situations here created the same triangles in different scales. So once we kind of establish that, kind of set that up there, then we can find that last missing variable using similar triangles. So, all right, that wraps up our last example. Let's go ahead and finish off our lecture. All right, so that finished up section 9.2. So in section 9.2, we learned how to identify types of triangles, find one missing angle in a triangle, use the Pythagorean theorem to find side lengths, and use similar triangles to find side lengths as well. So, all right, that wraps up our section, and I'll see you in the next one.